All right. Good morning. My name is Nick Larson, and today we are going to get back on some decision tree stuff. Today is May 31st, 2019. Um, yeah. So this week and last week we've been working on basically implementing some decision trees. The requirements are basically to make it fast. And we have been working and working and working. And yesterday we started making some real progress, and then we decided, hey, what if we decide to basically create an assembly, like a function, and then compile the function that just implements the decision tree as a bunch of if statements. And this is hopefully going to make it a lot faster, and I think it is going to. Did I update the information? I never update the information, do I? Whatever. Um, but yeah, let's take a look at that because it did work. We've had a lot of things on this project that have either gone well or not gone well, and I mean like really not gone well. Like large amounts of time where we did stuff and it just was completely worthless. But in this case, yeah, we had a breakthrough. So first, we had a breakthrough yesterday where we started off by switching the way that we do things, right? So initially, we were doing this where we would just pass in a single instance, and then we would evaluate the single instance, right? And what this does is it says, okay, go load up the tree and then perform this evaluation on this one instance. And then we would do this for all of the trees. This is a float array of about, I don't know, 1,000, linked 1,000, something like 850 to 1,000. It's large, but it's not crazy. And these trees are not super light. Some of these trees have as many as like 65 nodes. I mean, some of them get quite large. And each of the nodes takes up somewhere in the range of, well, let's just go take a look actually. 8 bytes it appears. So we've got 4 bytes and another 4 bytes. So 8 bytes and times 65, these things are actually kind of heavy, right? I would say the average number of nodes is around 50. And for any given tree, 50 times 16 bytes, no, times 8 bytes. I mean, they just get big, right? 50 times 8, what, 400 bytes being loaded up for every single one of our instances. And it turns out that this was the problem, right? That each of these trees are kind of heavy, and we're taking them out of memory, loading them into memory, and we're doing that 10,000 times. And that's a very not great idea. Instead, what we want to do is swap out the thing that's really cheap, which is just the array, and we can basically take all of the users at once, and we can, for any given tree, go calculate all of the user information. Now, here's the trick of this. When we evaluate a tree, we are almost always loading the entire tree, right? The path through the tree is taking like 6, and I think we found out that it's loading like 4 pages, like over 4 pages on average, between all of the instances. 4 pages is about, you're loading up 8 bytes at a time. So you're loading up 32. Oh, well, actually, now that's getting interesting. Oh, no, we were counting features. We were counting the number of features. So you're loading up 4 pages from your user vector on average per traversal through any given tree. Whereas with the job, no, with the if you can't tell, I didn't sleep well last night. I was having fun. I had a great day yesterday. The trees are the heavyweight part. We were taking them completely out of memory and then reloading them over and over and over and over and over again. By just taking one tree and then evaluating all of the people, we end up looking at far less memory. It turned out to be a lot faster. Then we said, okay, what if instead now we take the trees themselves and we just compile them, right? We turn them into a function. Holy cow, 63 people from C# Fritz. Oh my goodness. Welcome, everybody. I was just giving an introduction, but I'll go ahead and restart it. What's up, Rambling Geek? How's everybody doing? Thank you for the raid. I really, really appreciate that. That is incredible. All right, so just to sort of go over, and I'll just say the whole thing here so everybody can kind of see it. Thank you so much for the follow, Sarmad. I currently have a project where I get to work on stream, which is awesome because that doesn't happen very often. And what this job is if we go to Stack Overflow. Oh wait, I have to turn off my ad block. This is going to take just a second. So on Stack Overflow, you see that there are these jobs that sort of show up on the right-hand side. What we want to do is change the model for how we choose those jobs. So everyone on my team, hey, thank you so much. C. Payette, that is one of my first cheers. Thank you so much. Holy cow, that is awesome. Thank you. I really, really appreciate that. I also appreciate all of the follows. I will go through and say everybody's name in just a few moments after I get done with this explanation. Pie hole. Got to turn off the pie hole. Where is the pie hole? There it is. Disable. Disable. Custom time. 60 minutes. All right, yeah, on Stack Overflow, when you load up the page, what you get are these job ads on the side. The way these job ads work currently is a model that's about 2.5 years old, maybe even a little bit longer than that. And it's just a logistic regression. Super, super simple to calculate. The problem is every time we've tried to beat this model, we have not beaten this model. So we have tried for 2 years and then we just sort of give up on it and then we move on and do other stuff because we need to do other stuff. So this time around we sort of got some pressure from the team that runs the jobs and they're like, yeah, you know, there's a bunch of things like React and things like that where 2 years ago when we built the model, these things just weren't around. So they're not part of the model at all. And we don't actually do any sort of prediction for React. We only do prediction for JavaScript and like really big things 2 years ago. So instead, what we want to do is we want to switch out this model and we want to make it something that we can train all the time. So we all took a crack at it. The one that won was our data scientist, and it is a random forest. What a random forest is a bunch of decision trees, and a decision tree is basically a bunch of if-then statements. And it's funny because there is that one like XKCD where that's what it is. Oh, wow. Thank you, C. Payette. Thank you so much for the subscription. I really appreciate that. So decision trees, you know, that's the classic joke. AI is just a bunch of decision trees or just a bunch of if-then statements. But it's really like the interesting part of it is how you actually choose what those decision points should be. That's the machine learning part of it. I'm just like, I am completely floored right now by all the people following me. This is just really unbelievable. So thank you so much, everybody, for dropping in. All right, so as you have decision trees, and if you have a bunch of these decision trees together that all sort of vote on it, that's what a random forest is. It's just a bunch of switch statements. Ah, you're right. And so we started trying to look for a way to implement this, and the actual model was built in the R language. And so we said, okay, let's just make like an interface that uses R. You know, we won't have to do any translation. We won't screw anything up by having to implement it in C#, which is our normal language here at Stack Overflow. And the problem was the tooling that they have in R for like actually evaluating the decision trees was ridiculously slow. I mean, like atrociously slow. It was like for a single job to user combination, it took somewhere between like 10 milliseconds and 100 milliseconds for a single job. On our board at any given time, like if we go to Stack Overflow/jobs, you'll see that we have thousands of jobs. At this very moment where I'm at, you can see about, oh, well, it's running some sort of search. What is going on here? This was like 6,000 yesterday. Anyway, so this it ranges anywhere from like, I don't know, 4,000 to upwards of 10,000, depending on your location. A lot of jobs are targeted to only specific regions. I do work at Stack Overflow Rambling Geek. And I've been here for 8.5 years. It's been a long run. So we need to be able to do 10,000 of these in a short amount of time, like say 50 milliseconds or whatever it is. So the trick here is we need to basically take this thing that was taking 10 milliseconds to do a single job, and we need to do 10,000 in 50 milliseconds. So there was a lot of performance work to be done here. We decided to go with our bread and butter, switch it over to C#, start grinding away, start improving things, making things better. And that's sort of where we got. For the last like 2 weeks on stream, and you can go and visit my website and go watch all of the previous ones if you're interested in it. It's cultureofdevelopment.com, and you can click on streams, and it goes all the way back. The first one starts here, and I still have to, or starts right here, and I have to update all of this stuff for what I've been doing this week. So now we've made a lot of progress on this goal, and what we're going over today is some of the big advancements that got us from like basically changing the mindset of how we think about decision trees and how we think about solving this problem to thinking about the entire problem instead of just the one job to person instance. And we've made huge improvements. And if I run the benchmark, give me just a moment here and I'll pull up the benchmark. But if we run the benchmark, we'll see that for 10,000 jobs, we're now in the like right at 50 milliseconds range. So we've mostly achieved what we're trying to achieve. That's right. I know, Hugo. You've been with me the whole time, man. It has been a crazy go. And yes, we have gotten to 50 milliseconds for 10,000. We still have a little bit of room to improve, I think, and that's sort of just what I'm hoping to grind through today, but this is also really just a recap. So if we just run the benchmark here, it's going to take it maybe a minute. Yeah, a week ago it was at 300. Yeah, the very first time we ran this, when we started off doing like it, we started off at about 700 milliseconds for basically doing 10,000 of these. And we have slowly but surely grinded it down to doing right at 50 milliseconds. So this benchmark is only running 5,000. And it's going to run two different versions. It's going to run the first version, which is where we ended yesterday. And then we were trying to do the compilation stuff, and that's what actually streaming, and my computer is using a lot of its resources for that. Wow, C. Payette, you are really blowing me away, man. Okay, you know what? We got a minute here. Let's go back and take a look at some of these follows. Semaphore2, thank you for the follow. C. Payette, I really appreciate your cheers, your subscription. Oh, man, blowing me away. Grape, Johan B, Brave Cobra 2, Zerk, by the way. Piece of Pizza, I love that name. That's awesome. Jas Ariand, I'm not sure if I'm saying that right. I'm trying my hardest there. C17R, Hitface, Toongis, C Payette, Worldwake, C Sharp Fritz, thank you so much. I really appreciate that. Perry at Digital Ox, Surly Dev, and C Payette again with the actual with the extra 100. Wow, I'm blown away. Michael Jolly, 201. Thank you so much, Michael Jolly. Yeah, no. It's running the benchmark. If the benchmark ends up on the same processor as this, and here you see, all right, so this is running 5,000 and it's pinging in at 28. So if we multiply that times 2, it'd be 56. And that is where I'm at, like, while I'm streaming. So if it landed on the same processor for a few of those that it was doing the actual like stream encoding stuff on, that's where those big times are coming from. But that is it. Like, we have essentially achieved the performance goal that was set forth for us. And I'm super happy about that. So let's go over a couple of the big changes. The first one is when you have a decision tree, the way that a decision tree works, really the way that any machine learning model works, is you have a bunch of features, they go into a black box, it does some magic, it spits out a number, right? So the way that we did that is we described it. Thank you so much, Hugo Dahl, for the 1-month subscription. I really appreciate that. Coding Gorilla for the 202 bits. Oh, y'all are really blowing me away. This has just turned into, like, I love saying Happy Friday. This has been the happiest Friday for me so far. Thank y'all so much. So you have this model. You take in your features, which is like, you know, for this instance, it just happens to be like words that are in the text. Sweaty Omar, thank you so much for the follow. It happens to be like words that are in the text of a job listing, that are in the title of a job listing, the tags on the job listing, things of that nature. And then for the user, it's things like what country are you in, because we have to filter you out based on country for some jobs. What tags have you visited, and what percentage of your question views are in a given tag, things like that. And there's about, like I said, 850 or so features that come in. And so it goes in, it does all of these different decision trees. There's 1,000 trees that it does in this model. It sums all those together, and then it gives you a logistic value from that. And that logistic value is now a percent expectation that the person who is viewing this job, if we were to show it, whether they would click or not. Then we take all of those values, all of those percent chances, sum them all up, normalize them, and then we do a random selection through those, a weighted random selection based on their chance to click on each of those jobs. So any job you're allowed to see, you have a chance to see. There's a very large random component to it. And the idea is that, you know, we show you enough and we show you a little bit more often the things we think you're more likely to click on, but we still do some exploration around the other parts of the space. So when we started off, we basically said, okay, let's build a single job and a single user's feature set, send it into this decision tree, and then do it. And then we said, okay, now send it into 1,000 decision trees and do it. And then we said, okay, can we make this better? And we spent a lot of time this week looking at like decompilation using Intel vTune, also using, just bring that up again, vTune. We also used dot trace is another one that we used. All of these are like performance analyzers that basically take everything down to tell you how long is being spent on any given line in your code. And that line may be all the way down to assembly, which is what vTune is doing. Oh, and Rambling Geek with the 205, thank you so much. Goodness, I am floored. Thank y'all so much, this is amazing. JetBrains actually shows you line by line your actual code. So let's just go take a look at this. And you can actually see how much time was spent on each line of this thing as it ran. You can see that the number of executions for each line, stuff like this. And what it does is it shows you where the majority of the work is being done. So if we go take a look at this evaluate function, it literally shows you the code that it's spending the most amount of the time on. 84% of the time is spent in here. Oh, Michael Jolly, here goes. I'm just going to let these roll and kind of come back to it in a minute. But yeah, you can see here that it's spent 84% of the execution time in this single function, and this is how much time was spent on each line. Previously, this was not true. Previously, it was spending an enormous amount of time on this line, like over 50% of the time was being spent on this line right here. And my understanding at the time, my guess, was that okay, so it's trying to go and load these features from memory, and decision trees sort of choose a random feature in a sense. They're not random, they're selected based off of a metric, but they sort of jump around in the feature space. So the first one might look at feature 0, then the next one might look at feature 500, then the next one might look at feature 223. And the idea is that each of these things, because this feature vector is so long, live in a different page in memory. And so I tried to optimize this by reordering the features in the feature vector, right? So that in any given path through the tree, we would load the fewest number of pages. And so we spent a lot of time actually building out like an optimization algorithm that would go through and try to reorder them in a way such that it would minimize the total number of pages of memory that needed to be loaded in order to like walk through all of the trees. And we saw that it was loading about 4 pages on average, a little over 4 pages. And using the optimization algorithm, we managed to get that down to about 2.5. So we cut off about, 40%? Excuse me, we cut off about 40% of the number of memory accesses that should have been needed in order to get through all of the trees. Then we plugged it in and we reran it, and there was like an almost 0 improvement. And the idea was like, this should have been quite a huge improvement because we reduced the number of pages by like 50%. Going to load memory pages takes a very long time. If you were to scale up a single processor cycle to a second, in fact, there is a thing for this, scale up processor cycle to 1 second. Images. Nope. Performance equation. Latency at human scale. This is one of my favorite websites because it shows you this. If you were to scale up 1 CPU cycle to 1 second, then to go and access your level 1 cache would take about 2 seconds. To go and access your level 2 cache would take about 7 seconds, and to access your level 3 cache would take about 1 minute. Now, to put this into perspective, all 3 of these caches live on your processor, right? Which means that it can take up to 60 cycles to go and fetch something that's already on the processor. If you have to go all the way to the actual RAM, like physical device itself, you're now talking about 4 minutes to go and grab 1 page of memory from over there. Now, to be fair, when you grab a page of memory for your level 1 cache, it's only about 64 bytes. A level 2 cache page is significantly larger. A level 3 cache page is larger than that. And as we found out yesterday with the help of some people that came, Alpha Geek stopped by and corrected my misunderstanding, but on main memory, your pages are about 4 kilobytes. So when you go to load some main memory, you are bringing over 4 kilobytes to your level 3. Just period. That's how much you get, and it's all going to be sequential. When you load to your level 2, it's significantly less than that. When you load to your level 1, you're down to about 8 bytes. That's right. That's right. All right, just coming back. CPyet is up to 500 bits. Wow, thank you. Thank you so much. The Michael Jolly is in second place at 301. Rambling Geek is at 205. I'm just blown away by this. This is amazing. Thank y'all so much. Yeah, and as you like get to things that are slow, like going and talking to a hard drive, even an SSD literally takes days, right? Going and talking to a super fast SSD, like that is tied directly into the front side of the bus, not sitting back behind it, still takes hours, like in terms of how long you're waiting. So when you go and write something to your disk or you go and retrieve something from your disk, it takes an extremely long time. It's just really, really unbelievable. All right. And so that's why I'm trying to optimize this. This is why I thought, okay, we were going to reduce things from being like 7 seconds to being like 2 seconds. And this was going to make a huge improvement. That was my expectation. Ultramark, thank you so much for the follow. And when that did not happen, we had to come back and like rethink the problem. And at this point I said, let's look one step higher. Instead of looking at the decision tree, let's look at the model of all the decision trees and see what's going on. And what we ended up figuring out was that we are basically taking a single user and then we're bringing in every single decision tree. And these decision trees are not lightweight. They have maybe, I don't know, 64 different nodes in them, 65 different nodes in them. And so we're loading all of this data every single time we look at another job, right? And this is where this turns out to be where all of the data was being pushed around. And so we switched it. We rewrote the code, right? This is the original decision tree function, and this didn't actually change. We went one level higher to the decision tree model, where we were originally saying, okay, pass me in one instance. And then we said, what if we pass in all the instances and we evaluate all of the jobs for a single tree at a time? Oh, and not this one, it's this one. Right? So we take a single tree, then we evaluate all the jobs. And what we ended up with was a huge performance boost from the like 220 we were stuck at, and it dropped all the way down to about 130, 140, which is what you can actually see in that benchmark that we had just run. If you take this times 2, that's what that code is. That was the huge insight. And then as we were hanging out, Hugo Dahl yesterday, and maybe some other people who were here as well, had the idea, what if we pushed up, goodness me, someone had two people have new colors have broken 1,000. Wow, C. Payette and the Michael Jolly, thank you so much. I just don't even know what to say. I just can't thank you enough. I'm just like really, really out of my mind right now. So this was a huge insight. And then Hugo Dahl had, or I can't remember exactly who had the idea, but the idea is that at the very end of the tree, you are making a branch to basically go grab the value, right? And we said, what if we could take that last branch and we could just push it up and not have to do that last branch? And what that would do is basically save us one step, one memory lookup every single time we traverse through a tree. I didn't really know how we were going to achieve this, sticking with the way that we had it set up, which is basically super simple, right? We have this value. The value is the largest part of it. It's a float, and I can't change this value. Like, that needs to be how big the thing is. And the way that we branch is we basically say, okay, we just have one byte to tell you where to go. It's either left or right. And it basically skips you to another node in this tree. So as long as the tree has fewer than 256 nodes, everything should be fine. If it gets bigger, then obviously this is not going to work anymore. And so I wasn't sure how we were going to take this float value and basically shove it into the bytes. So instead, what I decided to do is take a look at a tool called Sigil. If you're not familiar with Sigil, Sigil is a tool... Oh, C#. Sigil is a tool that was actually written by my boss. His name is Kevin Montrose, and what it is a tool for basically creating functions and using a sort of easy to read way of going about it. There's a tool called, or not a tool. It's built into the .NET framework where you can actually emit raw IL. IL is the intermediate language that your C sharp or your F sharp or your whatever gets converted to, which then at runtime gets compiled by the JIT, which then turns into machine code, right? So you can just write this IL directly. And when you write the IL, then you can have it go and compile. So you can basically write functions as part of your running application. And that's exactly what we decided to do. And the tool that he wrote, Sigil, is basically a really simple way of doing it, that instead of having to know what the IL instructions are because they don't make a lot of sense, and let's just go take a look. .peak. If we take a look at this, and I just go grab some code here. Let's go to this one and this one. It's probably still going to be in there. I have no idea why these things take so long to load. Must be doing all kinds of magic. If we go take a look at this one, this one, this one, this one. Oh, look, we already have them in here. Okay, great. So if we go in here and we say, let's take a look at this decision tree thing, and we have this thing called eval. What do you mean? There it goes. All right, this is what the IL looks like, right? These are basically identifiers, just numbers. And then this is the actual instruction name. And there's hundreds of these instructions, maybe even thousands. I mean, this is a very specific instruction for loading a value of 0 into, like, onto the stack. This goes and looks up an element in an array at this index in this array pointer. This is a constant that gets loaded into a specific register. Stuff like this, right? And there's tons and tons and tons of these things, and knowing them isn't super simple. So there's this tool that basically says, I don't want to know what it is. I just want to say load this argument, and it's a constant of 0. Or no, load argument, which is an argument into the function, which would basically is getting whatever is passed in first. This is load argument second, which is grabbing whatever value is here. And then it's executing an add. And then it's saying return from this function whatever was the result of this add. And then you create a delegate, which is basically a function. You can then directly call this delegate, and you see that it prints out the result of adding these two numbers together. Right? Super, super interesting. Super, super easier to look at than knowing the actual instructions. Oh, thank you. I should really come back. Y'all are having some fun in here, aren't y'all? Unity does great posts on optimizing C#. Anyone claiming that C# can't be optimized is just wrong. More or less. There are some things that I do wish were a little bit easier, and a couple of them have actually come up on this project. For instance, if you want to drop down into pointer logic, it is extremely difficult if you're using like arrays of structs. In fact, you have to like really go through some hacks to even make that work. So what you end up doing is, instead of having like an array of you can't even grab a pointer to a two-dimensional array because the underlying storage for it stores the dimensions. Instead of it just being a bunch of things and you having to know what the dimensions are, it stores the dimensions. And so you can't just directly reference some part of it. You have to convert it into a single dimensional array and then grab a pointer to it. And then you have to do your own bounds checking. I mean, there's just like all kinds of insane stuff where it's like, I wish some of that stuff was just a lot easier, because it, you know, pointer math is super, super fast. Yeah, there are a few things that could still be improved, but more or less, you know, at the end of the day, everything gets compiled to the same machine instructions. The language itself is not really that interesting. I mean, not really that limiting, I guess I should say. The only thing that's limiting is the compiler. I'm over here following along 100% while just tinkering with MS Power Apps to fix my team's silly manual processes. Machine learning with actual computer science. What else could a man ask for? Yep, goofing around. I bet you can make a pretty good talk from all this. I have a lot of intentions of... I tweeted yesterday, I was like, I don't always sit around implementing data structures at work. That is not my job. But when I do, I usually learn a lot, and I'm probably going to blog about this one. But yeah, anyway, so to continue on the path here, so we decided to rewrite these decision trees as functions and then just call the functions directly. So the way that we went about this is the way that anybody would go about this, because I have never used Sigil prior to yesterday, frankly. So what we did is we came in here and we wrote a giant decision tree. Okay, let me see if I can find it. Did I lose it? I was really sure it was in here. I might have deleted it. I really hope I didn't. Oh wait, you know where it is? It's in here. File, open recent. Okay, so what we did is we literally took one of the trees and we wrote this evaluation function. This is LinkPad, by the way, if anyone's not familiar with it. This is one of my favorite tools for just like quick and dirty writing some C# and pressing a play button. You don't have to create a project. You don't have to do anything. You can write it as a script instead of a program, or you can write individual expressions. So I really love this tool. Rift87, thank you so much for the follow. So what we did is we wrote a bunch of if-then statements. That is literally what we did. And once we got done writing this, that's when we went to say, all right, what does this look like? Like, what should I be trying to create? And this is it. This is the eval function. And this is what the code looks like. So let's just go over a very small bit of it. If we go all the way up here to the top, it highlights it. You can see, first thing it does, features is arg1. So it loads the pointer or the reference to features onto the stack. Then it loads an index. We can see that the index in this case just happens to be 0, so it throws 0 on the stack. Then it goes and grabs the value out of the features array using load element. Then it loads this constant right here onto the stack. So we now have 2 values onto the stack, and then we branch based on whether the first one is greater than the second. So if this one is greater than the one behind it, right? This is greater than this. Then, even though this is a less than, the way that these are on the stack, this one happens first. The alternative is we could have done this load constant earlier on, but this load element right here is the expensive part. So you want to kick off the expensive part before you do the simple part. This is a single processor instruction. This one incurs the delay of actually going out and grabbing that memory. So you always want to do the most expensive things first, and then fill in the time gaps with the cheap things. This might actually get optimized by the JIT. I'm just not entirely sure. But in any case, we decided to write it like this. And then it branches, right? So if this is true, then we're going to go to IL10. Oh, sorry. If this is true, then this is false. So then we go to IL10. However, otherwise it just falls right through, loads this constant onto the stack, and then tries to return it. And so that's it. It actually turns out to be really simple. It's just this over and over and over and over again. So the way that you tell it to go somewhere is you create a thing called a label. These are labels right here, IL, whatever. These are labels for each and every single line, but you don't have to have a label for every line. You can actually create labels in your code very explicitly by literally just going to a line and saying, this is my label, right? And we have now created a label, and then any code after this, you know, some code int I equals 3, I equals 0. Now we can tell it to go to my label. Go to This is my label. Right? And now when it executes this instruction, it will basically branch right back to here. So instead of writing your for loops, instead of writing your if statements, you can do it like this. When you write it in IL, you have to do it like that, basically. I do not any... Oh, let's go back here. All right, it was either in LinkPad or the console app. Love, love, love LinkPad. Absolutely agree. LinkPad should be in everyone's toolbox. Can't wait to see what Joseph does with V6. Yeah, there's a lot of cool stuff coming out with C#, and I'm really hoping that it doesn't take long before it starts working in there. It's mostly just the syntax highlighting that sort of takes time. Go-to statements. Yeah, I don't actually write go-to statements very often, but when I do, they're usually in IL. All right, so that's what we're doing. We're basically saying, okay, let's copy this. Let's make this work. And it turns out to be pretty simple. All you do is you have one if statement, and then it takes you to the next node. You either have a left branch or you have a right branch, and that's all we're going to emulate here, right? So in our code, that's exactly what we do. We say, at the beginning, create a label that is basically the start, and then put in the first decision node right here. So create a label and then put in the decision node. Now what we're doing is we're saying, okay, if this is feature index -1 means it's a leaf and all we want to do is return a value, then that's what we want to do. Otherwise, we want to create a label for the left branch, create a label for the right branch, and then we want to put in the if statement that goes and grabs the feature value, loads the constant, does the branch greater than, and then we want to push onto the stack these two things that basically go out and say, okay, we need to write another if statement. We put those on the stack, and as long as the stack has nodes left to evaluate, then we're going to keep building out this function over and over and over and over again, and then when we're done, we just create the function. The first time you run it is actually quite slow because it has to go through the JIT. And when it goes through the JIT, you pay the cost of actual compilation. But the second time you run it, or the third time you run it, it ends up being enormously faster. And so that's all we did. We wrote this quick little thing that goes through, and then it runs a quick little test. This is just making sure that whatever random values we generated return the same values for all three of the methods that we have. The first one is the decision tree itself. The second one is the method that we wrote by hand, and the third one is the delegate that we wrote in using Sigil. And then what we did is we said, okay, how long are they taking? And we can see the one we wrote by hand still outperforms the one written by Sigil, but it's way faster than this decision tree. And so once we got to this one, the big picture is a little murky here still. You're creating C# code in the intermediate language. No, I'm creating the intermediate language and implementing a decision tree. There is no C# here other than I am using C# to create IL. So I am writing writing goto. I am writing IL using C#. And then I'm using C# to kick off a compile of that so that I now have a delegate. And I can call that delegate as if it were a function. So that's what DEL is, and you can literally call it exactly as if it were a function. This brings back the BCTASM memories. I have no idea what that is, unfortunately. Right. And so this actually, like in hindsight, achieves a lot of goals. Let's take a look at the decision tree itself. All right, so the decision tree itself, we were taking a lot of liberties. Like we had dropped this down to a float instead of having it be a double. The feature indexes were limited. Well, the feature indexes are always limited. But they are no longer limited to be shorts. We can now put on full integers in there, so we can handle a lot more feature indexes, or a lot bigger samples. Basically, the bytes for the true false or for the true branch and the false branch can now be as large as integers as well. So we can go all over the place. We have nothing stopping us here. All of these like things that we had to give up for performance previously have just disappeared. We can now support arbitrarily large trees with arbitrarily, well, not arbitrarily. We can go and do doubles in here instead of floats if we wanted to. And that's it. So then what we did is we tried that and we ran it, and again we saw that it was faster. So then we put it into the whole thing, and then we ran our benchmark, and our benchmark says we have basically achieved our goal. And that's basically like the insights that we came up with over the past few days to make all of this stuff enormously faster and get it within striking range of what we're doing. So what I need to do now is take a look at this code and sort of start getting it more ready for a production environment. Let's see, BC, Borland C, TASM, oh, Turbo Assembler. Okay, I do remember using, no, Turbo Pascal. That was the one that I was used to using. That was one of my first languages. I think I learned Visual Basic 3.0 first, and then after that, I moved on to Turbo Pascal, which I used for way too long. And then I think in high school I switched over to learning like C++. And then my last year of high school, I want to say, or very near my last year of high school, is when C#1 came out, and that's when I first started using C#. I remember doing some of that. Oh, would compile to ASM, and if you needed more speed, you would optimize individual routines using TASM. Almirana, thank you so much for the follow. I hope I'm saying that right. And the Michael Jolly, currently winning the bit war here. Thank you so much, man. Y'all are just like I'm just having the greatest day right now. Going over all of this stuff. Like, this was a long, hard 2 weeks. This was like doing all of this on stream. This is also like racking my brain. This is also like taking very long breaks of like just going and doing nothing to get my head off it and hoping that we can come up with something better. There was not like sitting down here and just grinding from start to finish. It was definitely like the breaks are what allowed us to relook at the problem in different ways and like look at a higher level and reorganize the way that we start processing through stuff. Like all of this stuff, take breaks. If you learn anything from this stream today, take breaks. That's it. Thank you for coming to my TED Talk. Shout out Robertables. Anyway, so yeah, now we have to get this ready for production a little bit better. The way that we're going to do that is on the server this will be running on. We basically don't allocate memory very often. We store a bunch of memory in pools of different things, and so I want to get this ready to basically handle that kind of stuff. I want to see if we take any penalty for not having floats, but instead going straight to doubles. There's a couple of things I want to take care of here. So the first things first is inside this function, Ultramark, thank you so much for the 100 bits. I really appreciate that. Goodness, we're talking about lasers. I have lost track. Oh, logo for the win. I've never used logo. I heard there was a turtle. Okay, so this is an allocation. We won't actually do this allocation. This logit is also allocating right here. There's no way that would be allowed. So let's fix this one first, because I think this one will actually be the easiest. We're just going to take this one, and it's going to take in... Actually, we're just going to pass in double. And we're just going to replace it in place. Now we don't need this at all. And we don't need that at all. And we just update this. And we no longer need this conversion because it's already a double. I noted that we could probably vectorize this, then I looked it up, and I don't think that you can do an EXP in a vectorized format It's certainly not in C#. How do we do that? Vector. Using system dot. Bring up my terminal, please. View terminal. Oh, that's right. It's this one. I learned that one yesterday. CD. What project are we in here? CD fast. Modeling. Oh, also, if you want to play around with any of this, it's on my GitHub, which you can find at GitHub. Bang GitHub. It's not in this JS13K one. It's in a project called Fast, which you can find on the Cultural Development main page. Fast.modeling, and then what I want to say is using, so .NET add package system.numerics. And then in here, yeah, vector should now be able to close this, open this. Vector. Okay, how about just using system.numerics? There we go. If we do vector double, it's just not giving me IntelliSense. That's lame. Every time I run into this problem, every time I like, or maybe I need to do like a .NET restore. Is that what the problem is? Now will it give it to me? No. I swear it just never figures this out. So we're just going to save this, close it, and reopen it. I run into this problem with VS Code all the time. I have no idea how to make that work. I'm just not getting it at all. I must have something wrong here. Oh wait, it's not system.numerics, is it? C# vector. Pop it over here. No, it is system.numerics. System.numerics.vectors? Can I NuGet. Oh, system.numerics.vectors. Okay. Fast.modeling. .NET remove package system.numerics. And then .NET add package system.numerics.vectors. System.numerics. Okay, vector. There we go. All right, yeah, it's got all of these instructions, but I could not for the life of me figure out how to get it to do an exp. So there is no exp function. I want to do math dot, like the equivalent of this but vectorized, and I couldn't figure out where that is, and I'm starting to think it's not even a thing. Yeah, so I just gave up on it. And so we're just going to eliminate that comment. Okay. What is next here? So this takes in a double of values. So this needs to go like this. This needs to be a double. This needs to be sums. Which really I should just call this result. Whatever, it's fine like that. Same exact thing here. This needs to be a double. There is no result. And this needs to be sums. Grab that Taylor series. I'm not sure I catch that reference. Is there a way to do this? Because that would be helpful. I mean, this isn't the slowest part of it, but it's definitely not fast. Okay, so that takes care of that. Then we need to pass in, all right, that gets rid of one allocation. Now we want to get rid of this other allocation because this would be passed in as a buffer. So let's just go ahead and pass it in as a buffer. Double result, double array, result buffer. And then that's not going to return anything either. So this becomes void. And then this one as well. Double array result buffer. This becomes void. Get rid of this allocation. No longer need that. Do your magic. All right, this doesn't actually allocate. Oh, it does right here. No, it doesn't. It returns a single value. Okay, so this one is still fine. This one doesn't allocate. This one doesn't allocate. Are there any allocations left in here? C. Payette, thank you again. I don't see off the top of my head any allocations here. I don't see any off the top of my head. Are there any allocations here? Are there any here? No. Okay, so these should be fine now. And now I want to talk about where we're going to start to deviate from what you would consider to be a typical decision tree to something that is more like what's going to actually work here. So these feature vectors, all right, Michael Jolly cannot be put behind, will not be put behind. All right, so the data that goes into these features, here's the thing about them is we have like say 10,000 jobs, but we really only have one user. And we're just taking that one user and we are comparing them against these 10,000 jobs. So what we don't need to do is replace that same memory, the first portion of the array, all of the parts of it that are specific to the user and only the user. We don't have to replace. We don't have to store in these instances. We can pass it in as a separate thing and then just have these instances be the job specific features. So this is going to be something like float array. And at this point, so I should make this very clear. At this point, I am now trying to solve my problem at work. This is no longer like, here's how decision trees should work or anything like that. This is like, I have a very specific kind of decision tree where my features are going to be passed in as two separate things. And I am solving that problem now. I am no longer in the realm of like, this is just a decision tree that is generic for anybody who would want to use it. This is specific to my use case. And so we're going to pass in a float array of user features, and this is going to be job features. So this is going to be a lot smaller. So this is going to be job features.length eval job features. But really, I want to change this function to additionally take in this user features stuff. Jess Sarian, thank you so much. I really appreciate you stopping by. I also really appreciate the follow, and I hope to see you again in the future. Thank you so much. Oh, here we go. I'm coming back. All right, grab that Taylor series. You can approximate the exponential function with polynomials, but I wouldn't use it to. But I wouldn't use that way to do it. Okay. Yeah, I really like this. This 100% comes down to speed, and if it's not a speed improvement, it's being tossed out the window. Like this is going into our app. Okay, so the user features, the job features. I now need to update this eval function to additionally take in the user features. So we're going to have to rewrite all of these. That is leet. Would the new async for each loop help here? Probably not. I would use an async when I am like limited, when I have latency issues, but I don't have latency issues here. This is entirely compute bound. So as long as the data is available, there might be a little, I don't know, the overhead of doing it as async is probably going to be more expensive than just waiting for the memory loads. Oh, that is right. Yeah, this has to be single threaded. So I forgot to mention that when I was giving the explanation earlier. But basically, this has to be single threaded. This runs effectively on a web tier, and so there are tons and tons and tons of requests. Somewhere in the neighborhood of maybe like peak hours, a few hundred, maybe 300-400 requests a second, split out over 3 machines. Each of these machines is pretty crazy. They're going to have, I don't know, 24 or 48 processors. Like, they have a ton of processors on these things. And so each one of these things has to be like single threaded. So all of this has to run on one processor. We did talk about splitting it up. We had this great conversation yesterday when we in our meeting, where basically what we have done by converting this into code is all of the trees now go into a different L1 register than the L1 registers for data. So there are instruction registers and there are data registers that are specific to each processor. And by converting these trees to code, we have taken them out of competing for the data register, and they're now competing for space in the instruction register. So while these are running, that's another reason why this sped up a fair amount, in all likelihood. That's our expectation. We have not verified that, but one of our tests shows that if we go to the point, so these registers are optimized for like wildly different things as well. The instruction register is optimized for not having things come in and out of it very quickly, whereas the so basically not replacing instruction sets that are in there, and the data registers are optimized for having things fly in and out of it quite fast. So what we did is we said, all right, we have these compiled trees. What if we do the old way and we say, give me a single user and run it against every tree? And that turns out to be enormously slow because it's fighting, constantly trying to swap out all of these compiled versions of the trees over and over and over and over again. And you're paying a huge penalty over there for that. And it turns out to be enormously slower when you do it that way, but it speeds things up like crazy when you look at just one tree at a time and you're not thrashing those registers. By swapping things in and out. Okay. Didn't you say it had to be single threaded? Yes, that is absolutely correct. That was one of the requirements. And so all of this had to be single threaded so that as these requests come in, they're not, it's not like one request is eating all the cores for a short amount of time. because that would basically just take down the entire server, which would not be good. Yeah, when this runs, I can't remember if this runs on 9 boxes or 3 boxes. I want to say it's across 9 boxes. So this is the work of this is being split up like request wise, and then each of these requests, the total request has like a 95th percentile of like 85 milliseconds. So we have to get all of this work done and then still do the rest of the web request work and get all of that done in 85 seconds. Yes. Okay, let's keep grinding through and see if we can get this to the point where we can hack this out. And then I want to see, I have an expectation that because we're not grinding through so much memory anymore, like of the 850 features, like 650 of them are user features. And only about 200 of them are job features, which means that this array is going to shrink in size massively. And this array is going to be accessed over and over and over and over again, which makes me think that what we're going to end up with is another performance boost by organizing our tests this way. And that's why I want to get through that on this stream if possible, but you know, that's streams go how streams go. Sometimes you get through with stuff you actually want to do, and sometimes you just talk and have fun. All right. So let's change our interface for all of these to include this. Evaluate probability, probability, probability. Our evaluate functions all need to take in the user features. Evaluate, evaluate, evaluate. Okay. Now we need to go to the trees themselves and rewrite the interface for the trees. This is going to break all of my tests when I try to compile, which is going to be awesome. So we're going to have to rewrite the test as well. And all of the evaluate functions need to take in a float array user features and float array job features. And we're going to go through and fix that in just a moment. All right, this is now going to take in another float array. This is going to take in, I'm just going to put job features here for now, but really what's going to happen is I need to say if node dot feature index is greater than user features dot length, then I want to say let's just say var features equals, we're just going to say user features, and then we're going to say if it's greater than the length. Actually, we're going to have to do a pretty big branch here. Have to do this twice. Okay. And then we're going to do the old else and move all of this in there. Okay, so the idea being that if the feature index is greater than user features.length, then we're going to look at the job features of this minus user features.length. Otherwise, we're going to look straight at the user features. Captain Reckham. Thank you so much for the follow. I really appreciate that. All right, so the idea, we did add an extra branch. We did add, in some cases, an extra mathematical number. But again, because we're grinding through so much less data, I have a feeling that this is still not going to like make it slower. I still think it should end up a little bit faster. If this one ends up being a little slower, then, you know, it is what it is. But we have... Oh, you know what's cool? When we do the compilation, we can literally bake this number. We already know the feature index when we're calculating it. We can tell it to load directly from this one or from this one. Wow, so the other one is guaranteed to not get slower. That's crazy. See, the compiling thing is awesome. Okay, so we fixed the interface for this evaluate. So half of these should be fine now, and we should only have 2 left that are complaining. All right, that one's fine. That one's fine. That one's fine. So now we just need to fix this one for the compiled trees. Okay. So how are we going to do that? We need to know right here which argument to load. So we need 2 arguments, and we need to know which argument to load, which is literally we can calculate right now. If node.featureIndex is greater than damn, we don't compile. I need to tell it how big. I need to tell it how big the first one's going to be up front. That kind of sucks. It's okay, we can do this. Int user features. User feature count. Okay, so we're going to have to pass that in. Is greater than user features count. Then else okay, so in this case it just is the user features, and we're looking directly at this. So we need to pop this in here as well. And in this case, we need this to be 1 for the job features. And we want to subtract out the user features count. There we go. All right, so that should take care of that one. And the idea here being that, all right, we're going to the job features. So we load in the job features, which are passed in second. And then we load in the index into them, which is the feature index minus the number of features that are actually user features. And then we go to, and then we just do everything as normal. If it turns out that it's a user feature that we want to look at, then we do exactly what we were previously doing. All right. All right. I think that's going to take care of it here. For the compile, the only thing is we have to know user feature count up front, which we already know from the model. True or false? True? We know the... No, it's just like a new parameter we're going to have to pass in. Okay, it's fine. It sort of just is what it is. This is really just about testing whether the speed is going to improve or not. Okay, that's fine. So eval user features job features compiled trees. Oh, why did my compiled trees not change? Right? This is... Uh-oh. Did I not save it? Compile. returns this. My delegate is exactly what I hoped it would be. Is this not the compile function? Oh, no. The compile function needs to pass in. Wait. This is just busted. Oh, no, it's not. No, it's not. It's my definition that's wrong. Right here. Okay, so now I need to compile them, and I'm just going to put in an arbitrary constant of 640 here. In fact, let's have that be not a constant, because that's awful. Int user features count. Okay. User features count. Okay. What's broken down here? Create int user features count. User features count. Okay. All right. Now everything's broken. All right, this feature reordering stuff was not valuable. So I'm probably going to just comment it out. Yeah. Or I could just put a constant somewhere. How about we just pass it in here? Int user features count. User features count. Man, when you make a change at like the core of your logic, my lord, you have to pull that all the way back out. That is the most frustrating part. Okay, I don't see any red on this file, so I'm just going to assume that it's good. That one looks good. That one looks good. Now the test. Ooh, that's a lot of red. Oh my. That's a lot of red. So now we're just going to have a constant up here, which I believe decision tree. Yep. I'm just going to do const int user features count equals 640. This is an arbitrarily chosen number, but it's not far off from the truth. Dot evaluate. I have an example test values. All right, test values now needs to become two things. Test values needs to be static float test user values. No, test job values equals new float array of 850 minus, I want to say it's 840, minus my user features count. And this is just user features count. And this is test user values. Okay. This is for the tree, the first tree, so I want to say something like if I is less than test user values dot length, then test values test user values, else test job values of I minus user feature count equals 0.1f. And then I have test user values equals 1.0. Okay. You could also return the count as a tuple element or ref from the load method. You could also return the count as a tuple element or ref from the load method. From the load method. In here? Where's the compile? When you load the file. Oh. Right. So the file itself, yeah, no, that's a good idea. It could be like the very first line or something. Where the hell is the file now? Datasets, XGBoost, the trees. So you mean in here? When you load the file in the test. 640. Oh, that's super interesting too. Well, I don't want to change this so much. This is actually outputted from R directly. Like when you save off the model, this is what you get. And so I don't really want to have to add a step to modify that file. There is another file that is not included here because I'm not allowed to show it to you that had the actual features in it, but there's no reason that in the feature list I couldn't just put a little marker saying that this is a user feature or a other one or a job feature. Yeah, there is another file here that has a list of all of the actual feature names. Right now they're all just renumbered to F732 or whatever. That's because I'm not allowed to show them to you. And the indexes that they are, like the line number that they are in the feature name file is where they actually come from. And so, yeah, I can't tell in this file, but in the other file, I could mark them as being a job feature, or really what I mean is a request specific feature or something that I can just leave in a pre-calculated vector somewhere. And it's those ones that are in the pre-calculated vector that I don't have to touch. And it's the specific ones to each request. That's what the first array is. The second array is the things that don't really change. Yeah, no, it's still a good suggestion. Like having just a constant floating around in the test is still kind of crappy. But again, this isn't the real values. This is me testing to see whether or not this is an actual improvement or not by restructuring the problem this way. If it turns out that we're not increasing the speed, then I'm going to throw away all this complexity. But the goal here is just to see if this actually makes it faster or does not make it faster. Okay, so we have these right here. I should probably just bump this back to 850 just to be safe. It doesn't matter if it's too big. It only matters if it's too small. Well, actually it does matter now because this is the one that I'm storing over and over and over again. So yeah, we'll just do 841 to be safe because I think there is a feature number 840 and it's 0 indexed. That's right. Yeah. That is exactly what I'm trying to test here. And unfortunately, I'm having to like rewrite freaking everything to do it. Maybe I'll just comment out all the tests. Yeah, maybe I'll just comment them out. Which ones do I need? Test decision tree evaluate. This is no longer going to work. We'll comment that out. Text create. Yep, nope, that one definitely needs to work. User features count. Test evaluate. Nope, that one's not going to work either. This is the one that's testing that the values are the values we actually expect, and that's not true. That's not going to work. Don't actually care about the reordering. This is good. I like commenting things out. Okay, evaluate timing. This is the one that we care about. So for this one, we want user features count. And then for this, I think what we need to do is get an actual example. Hey, what's up, Ganesh? Good to see you, man. I think we need to get an actual example here. So I'm going to say that the first one... Okay, I need to redo all of this. So the samples come in. We're going to say that the user features... All right, user features... equals new equals sample first dot value dot take user features count dot to array. Okay, that will get us some real values, some real user values for the features of the user. And then these, we need to say, something like, okay, var short job samples equals samples dot select m dot value dot skip user features count dot to array. So that is going to get us, and then we're going to say dot to array. All right, so this is now a float of job samples, and then we basically want to select this twice. Job samples. Basically want to select this twice, order it randomly, then we want to evaluate the probability, user features. Oh, I was really thinking that was going to work. Oh, I need a result buffer. Okay. Var results buffer equals new double to run dot length. And then results buffer. Results buffer. Okay. So this is just warm up. And then this is the real one. And that no longer pops out here. Okay, that's the real test that we care about. What's this thing? Test compiled func versus DT. I think for this test, we are just doing the compiled. That's really all I care about. So really what we're looking for is for this to be faster than about 50 milliseconds, or to be, yeah, faster than about 50 milliseconds. Okay. Compile. .NET build, C release. Does it build? Yes. All right. Let's get this going. Taher Yahia, thank you so much for the follow. I really appreciate that. I hope you're enjoying your day and having a good Friday. All right, ship it. That is absolutely true. How do we do this? Ship it. Boom. There we go. Ship it. Let's take a quick little swig of water. Save this, and then just cross your fingers, really. How do we run these? I forget. We go here. We copy this. We go to this one. XGBoost evaluate timing. Is that it? XGBoost evaluate timing. Come on. What in the hell? What just happened there? What? Let's see. Nope. Delete. Am I out of my mind? Test XGBoost evaluate timing. I am creating an XGBoost. When I do the evaluate timing, I am looking at the time compiled. I am so lost. This has been working the entire time. What if I just do it like this? Run test. Well, now it's doing it. Failed. Fun. Index was outside the bounds of the array. Okay. I mean, that's real. Index was outside the bounds of the array. My compilation is not working correctly. I'm saying take, I'm saying skip, I'm saying feature index, I'm saying that's got to be in here where we're doing the compilation. I'm saying if the feature index is greater than the user features count, greater than or equal to the user features count. It has to be that way because if the feature index were 1 and there were only one element, then it would only have an index of 0. Okay, I think that's it. Let's try this one more time. No. For some reason, .NET Test is just giving me all kinds of hell now. I guess we're just going to have to go back this way. Unfortunately, when we run it this way, it runs it in debug. Okay, compiling all of them. Ooh. That's sort of not what I expected. 80 milliseconds. That is a huge increase. It's difficult to tell. It's difficult to tell. Yeah. Oh, that's right. I'm in debug. Oh, God, yeah. Why can't I get this to run then? Okay, it's giving me problems. There is no argument that corresponds to the required. Oh, you know what this is? I am just gonna wait. Reorder mapping. 800. Nope. 640. That's awful. I can't do that. You know what? Nothing's calling this function. Is my answer. Oh, look at that. Get model. Reorder mapping. Int. User features count. Thank you for pointing that out. I was about to lose my mind. I would have thrown away all of this work. I would have. Oh, God, you're gonna make me do all of that again? Yep, you are. Yep, you are. Not sure why .NET Build didn't complain, though. It did not complain because I was in a folder specific to one project, and this... Oh, wait, no, that's a great point. It is in this project. What the hell? What? That's crazy. Was the logistic function you were trying to vectorize earlier? Yes, that is exactly what it is. Get model data path. Okay. Gonna come back and fix that later. I guess at this point I do have to make a for real decision about this. 640 it is. All right. Good talk. Now in here I have a user feature count. So we're going to say, actually, can I just copy and paste this? Where did we already do this? In the test? Here it is. User features. Should be able to hopefully just entirely copy and paste this. User features count. User features count. Result buffer. Now I should be able to say user features to run and results buffer. And this doesn't return anything anymore. Okay. cd.net build c release. It sort of makes sense why running that test didn't work anymore. The variable results is declared but never used. on program 9822, 98. Double results. Sure is. That's what I'm talking about. Let's try that one more time. Decision tree nodes. So these aren't decision tree nodes. This is the feature vector that gets passed into the decision tree and how wide it is. For a tree of depth 3, you'll never look at more than like, I don't know, 8. For a tree of depth 6, you'll never look at more than 32-ish, 64. But it's a random forest, so you have, thousands of these trees. Okay, now we're building. Now we're going to say cd space fast.modeling.test. And then we're going to run this. And I feel confident this time that it's going to run. Yeah, there we go. I'm confident. 61 milliseconds. Well, that's not 50 milliseconds. But I am streaming. Let's run it again. Oh, yeah. 64 kilobytes should be enough RAM for anything. Okay, so that seems pretty accurate. All right, I'm wondering how much of this is due to being on stream, or if passing in the extra arguments actually incurs additional overhead because you actually have to put those references now onto the stack. Maybe. Whatever. You're grinding through a lot less data. And we don't have to copy a bunch of data over. We have the job information separate from the user information. Now, instead of populating 10,000 times 840, we only have to populate literally 640 elements for each request. Okay, so even though there's possibly a little bit of a penalty here, I still think it's going to be an improvement in the long run. Run it on a second PC. I unfortunately don't have a second PC, and there's no way I'm going to RDP into one of my work machines while I'm on stream. In fact, I should probably even disconnect. So, how about I check it in, and then you can run it. I should branch this. I should put this in a branch. Repository, create branch. Commands, create branch. Production readiness. Commit. Work in progress. Reducing memory churn for production. The branch you're about to, create that branch. Do it. Oh, well. All right. The command that you need to run, just go into the folder fast.modeling.test and then run the command that's in the to-do. And don't forget that this is on a branch. All right. And that's it, really. That's all I'm going to do. It's Friday. I feel like from a production readiness standpoint, this has made a lot of improvements. It would be great if I could somehow find some magic to just pass in a single array instead of 2 arrays. Because then I could get rid of all of these changes to the decision tree itself. Just have the XGBoost be the thing. It's just way too much data. Like, let's think about how much data this just reduced. We have 10,000 times 640. We just got rid of 6 megabytes of churn from one request. That's a lot. That's a reduction of 640 divided by 840. That's a 76% reduction. So that's been a good improvement. I wonder if we can get rid of the trees altogether for the jobs. I'm sorry, if we can get rid of the jobs altogether. I don't know. Johan B, thank you. Hope you're having a good day. All right. Yeah, I'm going to go ahead and start wrapping this up. This was fun. Thank you so much for the raid, C# Fritz. I really appreciate it. That was amazing. I have had the most amazing day. This is the happiest of Fridays. Thank you so much, everybody. What I would like to do at this point is let's go find somebody to raid. Let's go find somebody to raid. Looks like Clark is up. Let's go raid Clark. Return the favor to Clarkio. He has raided me a few times. All right. Again, thank you everybody for stopping by. This was amazing. Got a lot of work done on this. I'm actually pretty happy with the amount of work we got done on the stream today. Running speed test now. I will hang out for just long enough to hear the results of running this speed test. In the meantime, yeah, when you get over there, just pop in, say hi to Clark, and give him a wave and whatnot. He's awesome. He actually built a couple of the tools that we're using here. If you want to like pop out line numbers and whatnot, he built this tool. And he's got a couple of other really interesting things going on. I'm not sure what he is working on today. It looks like he says he's writing tests for a new feature in Node.js. Okay, that's what he's doing. I don't know what that actually means, but we'll head over there in just a moment as soon as the speed test results come back. But yeah. This was good. This was so much fun. This was so much fun. 75 milliseconds. I don't know the specs of your machine. Yeah, I don't know I just don't know. Okay, well, I mean, it's a data point. As soon as I turn off the stream here, I'm going to check it again, and I'll post it in the chat. But, all right, we're going to go ahead and head over to Clark now. Again, just wave to him when you get there and whatnot. I don't have any, like, emotes or anything set up yet, so we're not ready for that. But thank you, everybody, for joining. Thank you for all of the follows. Thank you for all of the bits, and thank you for the subscription. Today was amazing. Oh, okay, you're on an i7-47. Okay, so I'm on an... I want to say I'm on an i7-6900K is the one I'm on. But I'll check the differences. I'm not sure. What you have may actually be closer to what's in production for us. All right. Thank you. We'll see y'all.